A mass spring system is forced to vibrate vertically at the resonant frequency of the system. The motion of the system is damped using a liquid. Okay, so this vibrator goes up and down, and the spring allows this thing to oscillate. And it says at time 0, the vibrator is switched on. At time B, the vibrator is switched off and the system comes to rest. The graph shows the variation of the vertical displacement of the system until time TB. So what are the questions? The first one says, explain with reference to energy in the system the amplitude of the oscillation between t equals 0 and t equals ta. Right? Well, this is pretty good, right? In terms with reference to the energy in the system. Okay? And so for this first region here, for this first region here, I got to turn into a pen again. Okay? The amplitude is increasing, right? Is increasing. I don't know how much they want, right? That's because it's getting energy from the vibrator, right? They say words like that in Britain, right? So it's getting energy faster than it dissipates it, right? Dissipates means for it to go away, turn into heat or something like that, then dissipated, right? So that's why the amplitude's increasing, right? And the reason that it's getting energy faster than it's dissipated is that the amplitude is still small, right? I don't know how much, it's only like how many marks, right? 2 marks or something like that, right? The amplitude's still small, so the damping force is small. The damping force typically is minus k times the velocity, right? So if the velocity is small, then the damping force will be small, right? So small amplitudes mean small velocity, therefore small damping force, right? And the k would be like sort of your damping factor, okay? So between 0 and Ta, the amplitude's still small. It's getting energy faster than it's dissipated, right? Since the amplitude's still small, the damping force is small and the amplitude increases. So let's look at the next question, right? It says from A to B, right? Well, from A to B, okay, the amplitude is constant, right? The energy is constant. It's receiving energy at the same rate equals dissipating, right? It's receiving energy at the same rate it's dissipating. Because if it dissipated faster than it received, it would decrease in amplitude. And if it received more than it dissipated, it would increase, right? But it's at equilibrium, okay? I don't know how much they want for that question, right? With reference to the energy, and I think we covered that, right? Okay, the system is critically damped. Draw on the graph on page 24 the variation displacement with time for TB until the system comes to a rest. Well, remember that critically damped means Q is 0.50. So that means in 1/2 of a cycle it returns to the origin, right? So here's half a cycle is from there to there. So it'll return to the origin roughly there, right? Not quite, but something like that, right? Okay. And you need to draw that on there. And don't forget, when you're doing these problems, if they say draw on the graph, by all means.